Hello everybody, thank you for clicking the channel of this video. I am Shusham. I have qualified CSIR NET in Mathematical Science on December 2017 and then I have finished my PhD from IIT Kharagpur and presently I am pursuing postdoc outside of India. But I wish to share my knowledge and experience with you about competitive exams, how you can proceed and how to learn. Many channels I have seen in YouTube, they are focusing on solving problems which are appeared in the previous year's questions. It's okay, by solving questions, if you understand, you can qualify NET exam. But what's next? After qualifying JRF or SRF, if you want to get admit in IITs or NITs, there is another round of written test which is followed by interview. So you need to learn the basic things. You should have a clear concept of the basic topic. Now I consider these are the important topics from my side, like linear algebra, real analysis, complex analysis, ordinary differential equation, partial differential equation and abstract algebra. Why do I consider these as the most important topic? Let's discuss. In CSIR NET, linear algebra contain marks of this, real analysis this range, complex analysis within this range, and followed by ODE, PD, abstract algebra. Suppose I score 50 in linear algebra, 40 from real analysis, 20 from complex analysis, 15 from OD, 10 from PD, 10 from abstract algebra. So what's my total score? 90, 110, 130, 145 out of 200. Is it bad? No. I can easily qualify JRF. Is it easy? No. Then everyone can crack CSIR NET in mathematical science. That's not happen. So to qualify this, you need a very clear and very efficient knowledge on some specific topics, not on all, only in some specific topics, and whatever I am considering these topics play vital roles not only in CSIR but cracking any competitive exams if you are a student of mathematics. And particularly in CSIR NET, there are 3 parts in question paper. You can see part A, part B, part C. I always like part C because there are 60 questions out of which I can answer only 20, each carrying 4.75 marks without negative marking. But there is a difficulty because the questions may have more than one answer and each and every answer perfectly you have to mark. Without this you would not get any marks from that question. In part B, it's MCQ type questions. There are options like out of 40 questions you have only 25 answers, but each carrying 3 marks. However, there is a negative marking 0.75 and it is MCQ type. Now part B and part C questions are coming from your subject area, that is from mathematics, but part A is general, it's common for all. It contains aptitude, reasoning, some general knowledge, so I am not going into this part. So earlier I have mentioned 140 out of 200, now not 200, it's 170. So you are good enough to crack JRF. So, but to get that, you should do hard work. Hard work never fails, as we all know. Now, start with the first thing, linear algebra. Linear algebra, why you need to study and why it is in the syllabus? Do you have any idea? If no, then I can say it plays a vital role. in any engineering and scientific field. Many nonlinear complex problems are linearized and then it is solved to get a nearby or approximate solution. That MATLAB software, many of you in engineering are using, also in masters it is now included. That full form of MATLAB is Matrix Laboratory. This matrix is associated with linear algebra. Then eigenvalues, eigenvectors, you all know its importance, that is also belongs to linear algebra. However, this linear algebra, that basic of this linear algebra, like a man stands on his feet, similarly a linear algebra stands on vector space. Now vector you have heard from school level, that is vector algebra, and it is based on unit vectors I hat, j hat and k hat. Whatever operations you do like dot product, cross product, everything is based on this, because any vector can be written like x1 I hat plus x2 j hat plus x3 k hat. This much knowledge earlier we had. So I guess that you know the definition of vector. If you don't know, please check on this. It's easy to revise. Then coming back to another property, vector addition, and that is called parallelogram law. Why is parallelogram? So there must be some parallelogram in that idea. Let's see. Suppose we have a vector x and we have another vector y. Since it is named as parallelogram, let me first draw a parallelogram. I am very bad in drawing, so please forgive me. This is the diagram. Parallelogram states that if x and y are these two vectors, then their resultant, that is x plus y, is given by the diagonal of the parallelogram. That's why the term parallelogram comes into picture. Another important thing is scalar multiplication. So addition you know now, that is by parallelogram law. Scalar multiplication. You have a vector x and if you multiply it by some scalar c, then either it is extended or it is squeezed. That is the role of scalar multiplication. There are other two compositions which are called external composition and internal composition. Now I am going slowly into vector spaces because these two compositions are related to a vector space. What is external composition? You see, if V and F are any two non-empty sets, then the mapping F from V cross V to V. So domain elements are like x comma alpha, where alpha is in F, x is in V, and codomain is V. Is said to be an external composition of V over F. What is internal composition? This is the mapping V cross V to F. So here the elements in domain are like x, y, x, y, both are in V. This is also referred to as vector addition. Now coming back to the definition of vector space. Stop some minute and you ask yourself, can you remind the definition of vector space? Many of you cannot remember, as it happens generally. So let's go through the definition of vector space. What it says? A vector space or linear space V over a field F consists of a set on which two operations, namely vector addition and scalar multiplication, are defined. Now, vector addition means your internal composition, vector addition, and it is written that for any x, y in V, x plus y must be in V. That is internal composition, because domain element contains two vectors. And scalar multiplication is your external composition for any A in F with x in V. There is a unique element AX in V. Still, these are two conditions. To become a vector space of a non-empty set over a field F, there are another 8 properties, like the vector must be commutative, they must satisfy associative rule, the set must contain an additive identity, for each element there must be an additive inverse, the set must contain a multiplicative identity, and for any two elements A, B from the field and x in V, A plus Bx equals to Ax plus Bx. AB x can be considered as A of Bx, and Ax plus y can be distributed as Ax plus Ay. Some examples I have given, those are very important in the study of vector space. Like we see, as I have told, vector space contains more than 3 elements. It may have dimension more than 3, or maybe n or infinite. So if F is a field, then F to the power n, which is n tuple, the elements are like this, is a vector space over the field F. Now field, you have studied in your undergrad. What are the fields? R, C, Q, these are all fields. So Rn is a vector space over R. Is Rn, or so if n equals to 1, then R is a vector space over R, I can say. Note that here n from natural number set and it is finite. So what we are discussing last, R is a vector space over R. E, R over C is a vector space. Think about it. But I am saying this is not, and you must keep in note f to the power n is a vector space over f to the power m, where m, n are from natural number set and both are finite. It is a vector space if m is less than n. Here it is not, because C can be written as R2. Hope you get it. Then next example, the set of all m cross n matrices over the field F, which is denoted by m cross n F, is a vector space over the field F. Now some more examples I have given here, like set of all functions from S to F. S is a non-empty set and F is a field, is a vector space under the vector addition and scalar multiplication. Also the set of all polynomials with coefficients from field F is a vector space under this operation. But remarkable thing is that there are sets on which additions, multiplications are defined, but they may not be a vector space. This kind of contradictory examples are very helpful in case of interview and also for competitive exams. So please go through this. So you know vector space and examples of vector space So simply you can now say what are the vector spaces. So V is a vector space, you know. If there is a subset of V, what can we say to it? W is a subset of V. Let's see. So now we are learning about vector subspace. Subspace means it's a subset of some given space. The definition is like a non-empty subset W over the field F is a subspace of V over the field F if W is a vector space over the field F under the operations of addition and scalar multiplication defined the V. Sorry. But suppose you have given a set like this under such certain condition and it is asked whether it is a subspace or not. Can you go through definition? By going through this definition is very difficult to answer in a short time. So there is a theorem which is very important. A non-empty set W is a subspace of V over the field F if the additive identity 0 is in W, W is closed under vector addition, W is closed under scalar multiplication. These two conditions can also be combined and it is written like this: for all x, y in W and scalars alpha, beta in F, alpha x plus beta y must be in W. Okay. Some examples like every vector space is a subspace over itself. So we can say V, non-empty set phi, these are all subspaces and these are called trivial subspaces. Then the set of all symmetric, asymmetric, diagonal, upper triangular matrices are subspaces over the field R. PNF, the set of all polynomials of degree less than or equals to n, that is the set A0, A1x plus dot dot plus an x to the power n, where A0, AI, you can say AI are in field F, is a subspace of Fx. But here the color looks like different. Why? Let's read. The set of all matrices in M n cross M, that is set of all rectangular matrices having non-negative entries. So matrix with entries, those are always greater or equals to zeros. Is not a subspace of the vector space, okay, M n cross n F, since it is not closed under scalar multiplication. You see, suppose you have a given matrix this and you multiplied it by scalar minus 1, then this scalar multiplication does not hold good in the given subset, so it is not a subspace. Fine. And also this is very important, like arbitrary intersection of subspaces of a vector space is a subspace, but arbitrary union, even finite union of subspaces of a vector space may not be a subspace of V. There are conditions W1 and W2. If two subspaces of a vector space V, then W1 union W2 is a subspace of V if and only one is contained in another. And another thing is, suppose you have given two subspaces W1 and W2, then W1 plus W2, which is defined like x plus y such that x in W1 and y in W2. W1 plus W2 is known as the smallest subspace of V containing both W1 and W2. So if someone generally asks you, I am giving you two subspaces, can you please tell me the smallest subspace which contains both W1 and W2? You must say W1 plus W2, not their intersection. Intersection does not always contain all the elements. Okay? Fine. Now coming back to some problems. Read first. Let M be the vector space of all 3 cross 3 real matrices. The problem I have organized like the topic just we have studied. Based on that, these problems are organized. So M is a 3 by 3 matrices and A is given like this. This is upper triangular matrix. I apologize for my handwriting. Now, which of the following are subspaces of M? So, you have to check. Suppose I do it the first one, rest you will check. What should we do? Assume W equals to X in M such that XA equals to AX. We have to check for alpha beta in F and XY in W whether implies alpha X plus beta Y in W or not. Let's check. Since X and Y in W, AX equals to XA, AY equals to YA. Now alpha X plus beta Y into A equals to alpha XA, just simply splitting beta YA. Alpha is a scalar. First we use this condition. AX equals to XA. So XA equals to AX. YA equals to AY. Fine. Now alpha beta is scalar, so we can write it as good. So we have got the answer. So A is a subspace of option A is a subspace. Option B I am leaving it up to you, but I am saying it is also a subspace. What about C? There is a property you must know for C. Trace of two matrices equals to trace of P plus trace of P. Using this property, you can check C is also a subspace. But what about D? D is not a subspace because determinant of the sum of two matrices not equals to determinant of the individuals. It can be checked. Suppose A equals to B. Determinant of 2A equals to 2 to the power n data. If, please note, this A is not same as this A. This is different. If A belongs to M n cross F, then this 2 to the power n will come. But determinant of A plus determinant of A equals to 2 determinant. Now these two are not equal. Hope you understand. So this is a question of marks 4.75. Let's see what is waiting for us. Let V1, V2 be subspaces of a vector space V. Okay. V1 is a subspace of V, V2 is a subspace of V. Which of the following is necessarily a subspace? Obviously A is a subspace. As I told you, arbitrary intersection of subspaces is a subspace. Union not necessary. V1 plus V2, yes, this is the smallest subspace containing both V1 and V2. What about D? I say no, because since V1 and V2 are both subspaces, so 0 element is in V1 and also 0 element is in V2. But 0 does not belongs to V1 by V2. So V1 by V2 is not a subspace. But this example is very interesting because you can check V1, V2 closed under addition and this is vector addition and scalar multiplication, but still it's not a subspace because of the additive identity element which is not present. So you understand this question with answers. Let's see what is next. As I have mentioned, which one of the following are subspaces of R3? R3 means 3 tuple x, y, z such that x, y, z is in R. First one is a subspace. You have to check like our first example. Suppose x1, y1, z1 and x2, y2, z2 belongs to W. Therefore, x1 equals to minus y1 and x2 equals to y2. Let alpha beta belongs to R. So alpha x1 y1 z1 plus beta x2 y2 z2 equals to alpha x1 plus beta x2 alpha y1 plus beta y2 alpha z1 plus beta z2. Fine. Simple algebra. Now what you have to check? We need to check alpha x1 plus beta x2 equals to minus alpha y1 plus beta y2 or not. Since these conditions hold, x1 equals to minus y1 and they are the elements of W. So let me change the color. This element matches with this element, similarly this matches with this. So it happens. So option A is correct. Now option B, what does it say? Class okay, this should be alpha x plus beta y, but this is not going to correct because x1 equals to y1, but here it's coming x minus y is 0. So this condition is not going to be true. So B is not a subspace. C and D are not because 0, 0, 0. That additive identity is not belongs to this set. So this is a question of 3 marks. Good. We are progressing very good. Hopefully this is the last question. Earlier one, which one of the subspace, and this is which one is not a subspace. Read questions carefully. That's why I have marked here. Which one is not a subspace of R3? This is Q3. Sorry. This is your Q3. Option A. And Q3 is a subspace of R3. Because Q3 itself a vector space over R, and Q is subspace of R, so Q3 is a subspace of R3. Or you can check as formal theorem. 0, 0, 0, if this is also a subspace of R3. This is trivial subspace. Which is not a subspace of R3. Oh, I made a mistake. You must comment whenever I made a mistake. This is a trivial subspace. A, B, real. So this is also a subspace. This is also a subspace. But question is which is not a subspace. This is, as I have told, this is Q3 is a vector space over Q. Q3 is not a vector space over R. Okay. How can I prove that? Because these 3 options are not true. Because C, if we write, C is your A plus B minus A plus 2B. So if we split C, and when in my next lecture I will discuss about dimension, you can see this is of dimension 2. So it's a subspace because you can easily check for any 2 elements. It is closed under addition. Also 0 is 0, 0 is in this set because AB are real. If AB are irrational, then this is not a subspace. But because they are real, this is a subspace. Similarly, this is a subspace. But A is not a subspace, which is what I am going to now discuss. What is A? A, B, C, such that A, B in C in Q. So it is simply Q3. Addition of 2 rational numbers is rational, fine. But this is not a subspace over R because not a subspace. Think about irrational numbers. Whenever you solve more questions, you will realize the misunderstanding in your knowledge, gapping in your, you can find the gap in your knowledge. That will lead to a good researcher if you find the gap. Suppose I consider minus ABC rational minus root 2 as a scalar in field R and multiplying it with the elements of W. this is belongs to W because all are rational. Then does not belongs to W. So the correct answer is. Thank you very much for spending this much time to listen this video, but I hope you will enjoy it and I will upload the next video. Obviously, if you motivate me to upload more videos, that's up to you. If you like it, please subscribe it, and thanks again for watching my